Okay, so the meshing is finished and our proxy is finished as well. Oh, so manual. One thing I think I'd like to adjust is that this curved section is coming maybe because our force is, if I template it like this, hide, maybe hide everything else. Let me put it here, maybe like this, okay. And if I bring in the mesh, no, it's hard to see like this. Let's try again. Uh, it's difficult to see like this, so we'll do like this. Template. I guess we are maybe a bit too low or a bit too strong, so it's creating this. Maybe it's like pushing too strong from the ship side. So probably we could just reduce this a bit more, or push it up a little bit further up, so it will not push the water first up and then down like we see here. Okay, but that's where we are going to experiment with these values. Now, I'm going to move forward to Whitewater. Okay, let's move this guy here. Let's open a new geometry node. We're going to call this one Whitewater Sim. Let's dive inside. Okay, so let's bring in our flip simulation, which is, we're going to call this in flip fields, maybe it makes more sense. Okay, pin, and then I'm going to go inside the water sim and I'm going to pull in the raw simulation. Okay, we can hide this one, dive inside. Now I'm going to create a whitewater source. I'm just going to plug this guy in here and let's see what it's going to give us if I press this out of the box. So now if I go to visualization and source particle, it's going to give me, say, at this frame I'm emitting these. So I'm going to play with the values a little bit. And then there's things like I don't want to emit, like this is the opposite side. And then maybe I don't want to make sure that I'm not emitting at this side as well. So that we can adjust this in several places, but I'd like to keep my sources clean. So we're going to do the cleanup here. Let's see if we need to maybe, doesn't hurt to have more. This is basically based on, if I turn this off and off here, and now it's going to say, emit only from curvature. So this calculates the curvature of the fields and then gives you some points we can emit from, which is fine. Now this is from acceleration based on, how fast accelerated and whatnot. I think this is all depends on the simulation detail as well, because if you start cranking it up, you'll start getting these repetitive patterns. Like I guess we can probably see one here if I keep doing that to make it maybe not that much yet. Now this is -1. If I go 1, maybe not here, but we can probably keep this, I don't know, 10, a bit more, a bit less. If I keep it at 1, it's going to emit all the time from all these areas. If I keep it at 10, it's more close to like when acceleration is a certain limit. Okay, vorticity, the blue one, so I'll go 10, more. Okay, so it's like a good mix, I suppose. Um, Now, what I don't need is, like I said, I don't need these edges, right? But the reality is that this is these points are not actually used. It's only for visualization. But you'll see here you can see the volume field. So for this shot, we can do a couple things. So we can do a little bit clamping using a volume wrangle or cleaning up, let's say. So here I'm gonna say, and the primitive name is emit. So I'm gonna say, hey, because I don't want to hit from the bottom of the tank as well. And again, this could be adjusted inside the flip solver as well, but I'm trying to minimize the disk size footprint as well. So I'm just gonna make everything as optimized as possible. copy so it doesn't bloat in the end. So here I'm saying anything deeper than 4 meters, emit is equal to 0. Okay. And now that's too much. So oh, maybe -4, sorry. Yes, -4 meters. So we did a little bit of culling there. That's fine. Now let's have a look from top view and shave off this edge and this edge. So this is going to be, let's say, volume bounce clean up. Now, there are several other ways to do this. We could create a bounding box and say, you know, it go 10% inside, and then multiply the VDB with the mask, but I'm just going to do it all in here. Okay, now the second one is going to be, I guess we could do on x-axis. So this is around whatever number this is. We're just going to go a little bit less, so maybe 30. So we can say that's x less than -30. Let's see if that takes care of that. It does. Okay, now let's get rid of the opposite. But this time bigger because on the plus side, and the value is probably, where is it? It's hard to judge. This second row, so it's like 2. But yeah, okay, so that's, let me double check. No, it's too much. It needs to be it's +2. Yeah. Okay, so we kind of did a little bit of a cleanup on this end, and that should give us a roughly good source. If anything, could be probably more. Let's make it a little bit more. So let's reduce our values a little bit so we get more coverage. Maybe I want 5. Okay, maybe I want 5 as well. Okay, cool. Now I'm just gonna put a null here again. So this is gonna go into caching because we can take advantage of multiple, like a PDG workflow here. So which means I'm gonna put a file cache. Oops. File cache comes down here. I'm gonna call this WWSRC. Again, we're gonna do the same thing like we did before. This is not a sim, doesn't have to be here anyway. We need the full range because we need to have a pre-roll on our Whitewater. Advanced, I'm gonna go copy the output file, copy parameter, go into here. Now this needs to start on a different branch than here, right? So I'm gonna put a rope geometry. So I don't need to put this task under meshing or Redshift proxy because it heavily relies on the full frame range of the flip sim because we're gonna do the full frame range, including the pre-roll. Now it's important to put the evaluate using single frame to automatic, so it won't try to do a iteration for each one of these. Okay, so what does that mean? Let me it might crash. So let me just save this. So if I leave it as single file, single frame, and if I do generate node, it's going to give me like what it's going to do, right? It's going to say, so this should be okay. For each one of these, it's going single frame. If I do a frame range, let's say if I do 901, then it's going to give me 2 frames per incoming frame. So it's best to leave it at automatic or frame range, I believe. Let's leave this to what it was, $f and. Now it's going to say basically cook node, not generate node. Okay, 1 source file per 1 frame of simulation. Okay, so let's paste this guy here. This is the output. You go up here. We're gonna call this, what should we call this? We'll call this WW source. Okay, so this guy comes here. This could be scheduled by both of my computers. If you're doing local, you just leave it as it is. So I'm not going to use the local scheduler. I'm going to use both. Oops, both. So I can split the tasks. Okay, and now we continue. Here is what I want rope geometry to be pulling to calculate to write out. It's not a sim. We can do like 10 frames. And that means like I'm going to launch Houdini, process 10 frames, and close it and open a new one. Okay. Now the best would be basically take the total amount of frame numbers and then divide it to the amount of computers you have. So you don't lose time opening and closing Houdini, but opening and closing Houdini sometimes for heavy operations is good as well because it will kind of clean up the memory for you. Okay, so let's continue. So the next thing we're gonna do, actually, you know what? We can launch this. This should go fairly quick, so we can work on the cache data. Okay. So what I'm gonna do is I'm gonna go here. I'm gonna run this, and hopefully it's not gonna explode. Okay. 6 jobs running, so I'm going to keep building while the information is coming, and then we can actually continue from there. So this, I'm gonna bypass this for now, so because I have one frame here. What I want to do here is now to basically create another null. And if I want to do something between the cache data, that will be my area. And this is www source volume, which is our emit. Now let's drop in a dot network. We're going to call this www solver. I'm going to change color to black. Okay, diving inside. Now let's go back up here, black. I'm going to make this round. Okay, dive inside. Now we're going to need a Whitewater solver. Okay, we're going to need a Whitewater object. And again, all of this is possible to access using shelf tools. I suggest you guys first try it out, see how it works, and then basically try to build it manually. Otherwise, a lot of mistakes are made, and it's very, very easy to skip important steps. So we're going to bring in our ship as well. Okie dokie. Now it's time to populate. We can call this guy particles, Whitewater particles. Now I'm going to give them a little bit of a bounce. So I'm going to jump to the physical. So 0.5 is too much. I'm going to reduce it. And then I'm going to add a bit more friction to them. Okay. Now this is my ship object. So let's populate that guy. We're going to have a gravity. I believe that's all we need here. Not this needs to be left input. That's correct. Collide relationship, all good. We need to bring in our ship here. Which is going to be brought in here because we need it. So let's put an object merge. And let's bring in our ship. So we'll call this in ship. Okay, and that is going to be into this object, going into outfollow in the prep Missouri here. It was this one. Oh, it was this one. Well, it's the same. You could use whatever you want. Just the output geometry. Okay, let's go back to here. Now, what I'm doing here is I'm going to take, so the geometry is going to go inside. This doesn't have velocities, so I guess that's where I'm using it. So let's put a trail sop to get velocities onto the points. Okay, that's fine. Now I'm I'm going to create VDB from polygons with a voxel size of 2. Okay, and this is my VDB ship. Surface is fine. Now I'm gonna call this WW VDB call. Okay, and I'm gonna call this guy VDB WW geo call. So one of them is a geo collision, the other one is a VDB. Okay, all goes inside the same sim, so we're gonna give them all the same color. So there's a relationship there. Go inside. Uh, Now let's populate these sections. So geometry goes into sub path. I would like to be, this is a deforming, so it's changing per frame. Now I'd like to be able to reevaluate SOPs to interpolate geometry. That's perfectly possible here because the geometry exists. Now if I go back inside my physical attributes, I can play around so there's like a multiplier against the, the solver particles. If I go switch to the collision tab, I can switch my mode to volume sample, which the size which is 0.2, but you don't need to change that. And then I'm just going to drag and drop this into proxy volume. Okay, to make sure that my particles are, going to be okay. So now, anything else? Yes, the volume source. If you do a mouse over, is the path to stop not providing the source volumes. There you go, liquid, which is this one. So this comes in here. Now the emission source is the output of this, which is this. Okay, and then rest is pretty much the settings. So whitewater scale is separation between the nearby whitewater particles. So it's like more particles, less particles. And then the voxel size is the density of the volume. And it works for, it says here repellent seeding, so on and so forth. So and there's actually a value that says voxel size should be at least twice as large as the whitewater scale. So we're going to test these values, but first it says at least, so we're going to leave it like this. So it's not twice, but it's more than twice, but I actually keep it, I believe. I think that should be all right. Now, we're going to play with the emission amount to see how much we need to emit. And then we're going to play with the initial speed and, all that extra stuff to play around. But I always add some noise to it, really. The limits are important. So I'm going to use the same thing. I'm going to actually, no, let's go back here, pin it. So we're going to go back to our sim and go back to our bounds and do the same thing here. So limit size, copy, paste, and then the center, copy, paste, back to Whitewater sim. By the way, our source is finished. Let's double check if it's okay. Let's turn this back on, visualize, load from disk, scrub. Yes, we have our source. Yeah, we can shave the back of the source as well. I think there's a line every now and then. I think it's okay. I guess then this just allows us to test right now. Simulation starts at 900. I'm going to disable this so it goes a bit faster for now. Press play and we should get particles, but depends on how many particles we get. We need to do some setting changes. Okay, so it's emitting, so that's what we want to see first. So I'm going to go to foam settings and I'm going to turn off a couple things to speed things up. I'm going to turn off density control. I'm going to leave repellents and depth control by default. I am going to make the size of the repellents much smaller, I believe, because of the scale of our object. So if I go to first frame here, you'll see that these are our repellents, okay? And I believe I changed my fusor size to something from very small to something even more, instead of 0.9 to 0.5, and then my strength range is a lot more than what is out there. And I believe I turned on the mesh radius distribution as well. So what does this does is that it kind of does an ununiform distribution. Uh, okay, what else? I don't think I have anything else turned on. You can always play with these values, but um, we're just building the generic setup here. So let me go back, and if I press play, so we're gonna get some particles. Now, some of these are foam, some of these are uh, different qualities. So if you turn on color particles by depth, then you're gonna get, the green is the spray, I believe red is the bubbles, and white is the foam. Okay, and so far so good. This is working. And now I need to enable my collider, of course, and press play. Okay, at the moment this is working, and the camera is going to keep going forward, so I'm not going to remove particles from the system here, but we could also do a little bit of an optimization here, I believe. Let me see how that works out. I think I haven't done it on this one, but there is some room for optimization here. So I'm going to jump into my mist solver, and we're going to try to do that camera clipping method. Okay. All right. So the extra sources particle, I think we could do it in the post solve. It's worth a try. All right. So let's put a geometry angle. Okay, and let's call this call by cam. Okay, so I'm going to plug this in here. So this is I found this on the internet for some long time ago. So we are getting the basically we're gonna get the camera. Okay, let me actually put the camera here. Type properties, no, edit parameter interface. So I need a operator path, and that's gonna be my camera. Or is the yeah, it's the operator path. This is the selection one. Yes. So I'm gonna select the camera here, which is my render camera. Okay. Let's change the renders. Let's just the label as well to something that makes more sense. Let's call it cam node. Cam node. Okay, so from world space, and this is gonna convert the camera to camera space. Okay, so we can type vector ndc. Okay, actually, let me do like this so we could see what it's doing. V at ndc equals to ndc. Okay, so if I open the parentheses here, it will tell us transforms a position into normal device coordinates. So it's going to figure out where it is in terms of camera space. And so which means that here we're going to supply the camera, which is our camera node attribute, right? We're going to feed in the position. Now, if I do just this and then pick my camera here and just do a frame forward, I believe if I open geometry selection here, we should get NDC, and it should be from 0 to 1. These are for the ones that are outside. I think that should be correct. Okay, now I'm gonna create a little bit of a padding. Okay, and at the end I'm going to credit this guy as well who put this code here, but we're gonna go step by step as well. So this is just a padding that is just creating a value that we can shift around. Okay, now what he does is creating a little condition here called if condition. Okay, and then it's saying NDC 0, which is this guy, right? Minus our padding, or so in Vex, this is and, right? And this is or. Okay, so for all axes, right? But now what we need to do is that because he's not declaring this, he's using it temporary, so we need to revert this to vector. all the NDCs. So this should kind of work. Now let me see. Did we skip something? Oh, we have a little typo somewhere, I guess. Oh, vector. Okay, and I want this to run on maybe not all the particles, but okay, actually, if you see, it's already working because we're not looking from the camera, but if you zoom out, I think it's on the, emitting from here, and that should be the edge of our camera with the padding, which is 0 at the moment. But if you look here, we have white particles here, but not of the camera angle, right? So if I can add 1 meter, go back. Okay, we remove too much, maybe we do, this is too much, I suppose, but if we do like this, let me see. Okay, that's maybe a little, oh, it's fine. It's like just behind the camera. So it's kind of like instead of simulating all this stuff, because our ship is moving forward and everything we see is going backwards. So we're never going to see what's happening behind the camera throughout the frame range. So which means that we don't need to calculate if there's like 1 million particles here, we don't need to calculate this other 1 million here because why? We'll never see it, right? So which means that we are saving a lot of memory here and possibly speed. This is not a very expensive operation. If we want to see, I guess we could always do a little comparison. I'm gonna go rest. Maybe in the small amount of particles, probably not gonna make much difference, but we can see what the cost of that solver. So it's in here, and basically it's pretty much nothing in comparison to solver, right? So that's a good I think sacrifice here. Okay, so now, but usually when you optimize things, then you basically want more particles. So this is where you can go emission. Maybe we go 10. Okay, so I'm not doing this anymore. If I press play, now I'm gonna get more particles in that emission area. Okay, so this is working. Now what I'm gonna do is I'm gonna leave it as it is like this and continue down to cache this out. Now I'm gonna drop down and import uh, dop import fields. Okay, and what we're doing, yes, we're gonna update these fields now. So on the dot network, oh, that's this guy. Just pin this, go inside, select your particles, because if you don't do that, it's gonna pull in the collision geometry and all the additional fields as well. So all we're interested in is new particles, right? So this is import Whitewater. Okay. Now, what do I want to come out from here? So if I select this guy, oh, sorry, here you can select particles. Okay, by default, that's just geometry. I'm not going to use any of this here. I'm just going to go frame forward. So put some stuff out. Okay. Now, this part is, I think, quite important and mostly skip. It's very important to do a good cleanup. So let's make sure that we get rid of anything we don't need. Okay, so drop in an attribute delete. Okay, and let's get rid of everything we don't need. So I think all of this, if there's anything, okay, there's going to be a group. We'll delete some of the groups. And here I'm interested in keeping velocity. I'm interested in keeping, I guess, I'm interested in keeping depth. So let me see if this is already here. We did. If you don't add the state attribute, you can always use the depth attribute. Okay. So state attribute is going to output 3 attributes. called spray, bubble, and foam. If you keep it at nothing, you'll get a depth attribute which allows you to differentiate between spray and bubble. But just to keep things a bit simple, we're going to add the state attribute so we can pick between the types. So I'm going to keep not depth. Let's go another frame. I'm going to keep bubble, spray. I'm going to keep ID definitely. And I'm going to keep foam and age in case I need any of this, which means I want to keep this. So asterisk and shift 6. Okay. Still a little bit too much to my taste. I think we could keep on the depth because keeping on the depth will get rid of these 3 attributes. So it's a good savings. And I do not need the group delete. For storage, I don't need any of this. Okay. Saves a little bit of space. But when you have dealing with tens of thousands of points, it's a good saving. So let's put an add sub. Now, the reason I'm doing that is here is just unconnected points. You can use an add point, go to particle tab, and then at particle system. Now is a particle system. So some renderers do care about it. Now, what I'm also going to do now is that I'm going to convert these particles to VDBs. Convert VDB points. Now that's great for storage because you can pack them. They look black here, so I'm just going to put the background to light. Okay, they turn black, but then we can do a little bit of a compression. We could do we pack them using voxels, and then I guess we can do like if there's a color, you can compression if there are other compression methods, or you could do, for example, I guess we want to get rid of, we want to squeeze the bubbles a little bit. We could do, a little bit of here, a little bit of there. It will save the will save a lot of information from spray, and we can do a little bit of a, I think, comparison as well. I guess we don't want to change the IDs just in case. I'm gonna go a little bit aggressive on this and put a null, call it ww sim. Now, I guess let's do a little test. I'm just gonna let it run for a little bit, so we got a little bit more points. Maybe it will make a bit more difference. So let it cook for a while. Okay. All right, it's not that much, but we'll see. So file cache, call it ww sim. I'll call this out ww sim because this one is for reading. Okay, same like a bow, load. Now let's do a little test. If I say, I think, now leave this as it is. This is a simulation. I'm gonna save this one here, save geometry. Let's do a little test. Let's call it PTVDB. Should be here, PTVDB, this is 2 megabytes. Let's do the same thing, I guess, here. Save geometry, PT only. And that one is, so the same thing before compression and everything. From 9.7 megabyte, it went down to 2 megabytes. So that's good savings. Now, what did we destroy so much? Well, maybe we can have a little comparison because there has to be a takeaway, right? If the numbers change so much. So this is particles as they are. This is VDBs as they are. So now, um, first issue is Mantra doesn't support, or Redshift doesn't support rendering VDB points out of the box. So you need to unpack them. VDB convert, which means you can't do, you have to write it somewhere or some processing involved before actually using them. Extract points. Okay, so now I'm gonna switch back to black background, and we did something with those attributes, so it's probably worth having a look. Maybe there's a little change in the values. So maybe we put a colors up here. What did we compressed? We even compressed velocities. I think maybe velocities will be the best to see if there's going to be a difference. So these are the velocities here, and these are the velocities here. So that did make, I think, a lot of difference. Oh, not here, sorry. Here. Okay, so, oh, because we actually pushed it a little bit too much, 8-bit unit. So maybe we should not compress. Let's try 16-bit. I'm just going to try this again. Save geometry, VDB. So that was, let's call it VDB2. So VDB2 is slightly bigger file. What happened? Let's see if that is breaking us as well completely or not. Hide all attributes. That's going to be V. So -8 to 4. So this is some really big changes here. So that's probably not okay. This is definitely breaking it. What is this one? This one I don't know actually. We're to try. Maybe it's not really good to compress the vector attributes. Okay, I'm gonna go 8-bit fixed point, and I'm gonna remove the V. Let's check the other attributes to see how much of a difference there is, like a bubble. So this is color again, ramp. I'm gonna turn this off, say bubble. So these are the bubbles. Okay, it's just like telling us what is what. Pretty much the same thing. But what happens if we not compress the velocities? So that's VDB3. And VDB3 is even smaller. Is it because we're not storing it? No, this cannot be. Okay, we do want to keep the velocities here. Actually, we could. So which one is slower then? Since we're gonna process this and I have the IDs, why don't we create a trail sop and recalculate the IDs? We should have the IDs. We didn't store the IDs. All attributes, attribute transfer, all attributes. I'm gonna go. Okay, okay. So this is actually. I think we should leave this at all attributes. Otherwise, we're removing attributes. I'm gonna try this as VDB4. Okay, this one is gonna be bigger now, I guess. Okay, half size still. Do we have what we need? That's more important. Okay, so we do have the velocities. That's good. So we don't need this anymore. And They are healthy. Okay, well, at the worst case scenario, by just offsetting the positions to 8-bit fixed point, um, we just half the file size, right? And to be frank, I think I'm going to go with not bubble, spray, or ID form, but just depth. Okay, depth. Let's do it again. Save geometry PTVDB4. Reload. Let's check the file size now. VDB4. Okay, we're 4 megabytes. Okay, so we did achieve more than 50% of compression, and we do have all the attributes we need. Almost zero visual uh, quality loss. Okay, now we need to cache this out, obviously. We go down again. Let's save our scene. Okay, so we did cache this out, right? So this is the source. So we need to simulate this as well, which can happen in parallel to everything else because none of these other guys are a dependency. So I'm going to put a geometry node again. Okay, and this is going to be set to automatic. No, not this one, sorry. Drop geometry output. So this is going to be set to automatic. And this goes in here. We're going to call this WWSim like the other ones. I'm just going to pin this, go back to my sim network, drag and drop my out WWSim into my SOP path again. Now I want to write to the position that I'll be reading from, which is like this, right? But in the advanced path, we have the output file exposed, copy, paste the output file. Now the important thing is to set simulation, just to make sure that this is because it's supposed to be a simulation. Okay, and now the next thing we're gonna do is exporting this as RS proxy. But this is a little bit of trick that we had to do because of the edge compression that we did on the meshes. So we have to apply the same thing. So before we can do that, we need to cache it out so we can do it on the in the process as we have the access to data. Okay, so let's put this down here. Let's call this Whitewater simulation. Okay, and let's go back to here, and I'm gonna save. Now this one scheduler, you can select local scheduler if you have one. Again, I'm gonna change my workstation, and now because set to automatic is gonna go for this many frames, not 176 times 176 times 176, but it's always good to do a generate node check. That's healthy. Save and sim. Right, I'll see you in the next video, which is gonna be what is gonna be. It's gonna be where we are gonna do our little bit of mist simulation or a little additional spray. Thank you.